Welcome to this video where I'm going to be discussing several examples on rigid body hydrodynamics using HYDRAN-XR. Now, HYDRAN-XR comes with several test problems, and if we go to the downloads folder on the website, we can download the input files for these test problems under the link example files. If you download the linked file, and expand it, you'll create a folder called testing, which contains several subfolders. And we're going to be discussing the problems in the examples subfolder here. Now, let's start up HYDRAN-XR, and I've already specified what the working directory is and what the project name is. So what I wanted to look at right now is this first problem we're going to be talking about is in the introduction PDF about let me come back up here. That's where it was last left off. Let me just make that a little, maybe that's not too, let's come back here. So this is a short PDF on introducing the basics of HYDRAN-XR. Not really how to use it so much, but it does have, if we scroll down here, it has several examples that talks about. So into 11, here we go. So this is basically the problem we're going to be solving. It's a simple example of the rigid body motion of a single rigid body. And the body's a rectangular box with dimensions of 90 meters by 90 meters and a draft of 40 meters. And it's freely floating in deep water. Now, this problem is kind of a classic problem that was introduced by Fultonson and Michelson in 1974. So there's a little bit of a description of it here in this file, but we're going to be talking about it in a lot more detail in this video. So let me just hide that and come back to here. Now, the two input files that are relevant for this first case is box0.txt and box0gen.txt. The 0 just means we're not going to be using symmetry. The box is doubly symmetric, so we can either use no symmetry, or we can use single symmetry, or we can use double symmetry. So in this file, we're not using any symmetry. And I've already got that open here. Now, I want to go through these commands one by one. And this file right here is the main input file. It can be used for any rigid body hydrodynamic analysis with just some minor changes, as will become apparent as we talk about it. If you have a question about a command, you can refer to the PDF command reference document, which sometimes I do, but honestly, mostly I reference the text file, help file, which is also available on the website here. And coming back to that, and I used H for the shorthand for help to generate this file for each command. So the first command, if you'll recall, is hide parameters. All the hydrodynamic commands start with a hide underscore or a phide underscore for print. So if we come here and we search for hide help on the hide parameters, we can see what all the particular parameters are. And if something is in brackets here, it means it's optional. So one thing that is not optional is the water depth. It does need to know what the water depth is. And there are defaults for some of these other parameters, for all the other parameters actually. And we're going to be taking the defaults for most of these guys. But anyway, we're specifying this to be in 5,000 meters of water. Now, that just means essentially it's deep water. I mean, so if the water depth is quote unquote deep relative to the wavelength, then it uses the deep water formulation. Symmetry equals 0 says we're not going to be using any symmetry, and in mode R equals 6. In mode R is the number of, in this case, rigid body modes, and so those are the 6 rigid body modes: surge, sway, heave, roll, pitch, yaw, that we're going to be looking at, because this is a rigid body analysis. The next command, hide chord axis, really specifies the body fixed coordinate system. So HYDRAN-XR uses an inertial coordinate system, the origin of which is always at the still water line, and then a body fixed coordinate system for which the motions are defined. So ZB tells it where the origin of the Z location of the body fixed coordinate origin in the inertial coordinate system axis. So this says ZB is equal to 0. In other words, the body fixed coordinate system is at the origin of the inertial coordinate system as well. And ZCG says where is the body CG in the body fixed coordinate system. So in this case, because the body fixed coordinate system has an origin at the still water line, this says that the center of gravity is 10.62 meters below the still water line. The next command defines the wave angles and the wave periods. So in beta equal, so we're going to be using 2 wave angles and 8 wave periods or frequencies. In this case, we're inputting frequencies, or excuse me, periods. Even though it says the ID shows it says frequencies. One can either input periods or frequencies, but the syntax we're using here is for periods. You can refer to the manual if you want to use if you want to input frequencies and see how you do that. So we're going to be looking at 0 degrees and 45 degree waves. Now 0 degrees means that the wave is propagating in the plus x direction, and then 45 degrees comes from the right hand rule about the z-axis. So we're looking at 8 periods ranging from an 8-second wave to a 22-second wave. Now this is a very coarse discretization, or delta t, and that's just to make the calculations fast, so we're only doing 8 periods. Normally in a practical problem you'd want to use a finer resolution. The next command, file in, says, okay, read in this next file, box0-gen.txt, which defines the mesh. So if we look in here, in that file, we see that we specify the nodal coordinates. There are 57 nodes, 1 through 57, and this is the x, y, z coordinates. There's another alternative syntax for the input for these nodal coordinates, which we'll see in a little bit, but this is one basic syntax, which essentially requires the x and y and z coordinates all to be specified. A couple of nodes here have been, this node is really supposed to be on the still water plane, but I've put it slightly above the still water plane just for demonstration purposes, and we'll look in a little bit where that comes into play. And this one similarly is slightly below the still water plane. Again, it's supposed to be on the still water plane. And then the command hide node tolerance, which we'll get to and which is related to these 2 nodes here. So basically what it does is it fixes nodes that are supposed to be either on the still water plane or on planes of symmetry, but because of whatever reason there's tiny errors that popped in that are under some tolerance that we can specify here. Here we're using the default tolerances, but then it'll fix the nodes, as we'll see. And then we define the panels. There's 48 panels. So this is the panel ID, and then the 4 node numbers defining the panels. So p hide nodes and p hide panel will print the nodes and print the panels. You may or may not want to do that. I mean, for a large problem, you're going to get a lot of output. It's only to the output file, not to the screen when you're doing this interactively, but nevertheless it could cause quite a bit of output.
Hide export graphics is a command which exports a .msh file where we can view the mesh, and so we're going to be looking at that. Hide body check is a command which should not be overlooked. It should be done, and it does some very basic checks on the panel mesh, and you should check the output for that to make sure that it's calculating correct values. If it's not calculating correct values, it means there's an error in your mesh. There may still be an error in your mesh, but this is doing some basic checks. Hide rigid modes generates the 6 rigid body modes. HYDRAN mass allows one to specify the 6x6 rigid body mass matrix. Here, this is of course the mass of the structure here, should be equal to the displaced volume, of course, unless, especially, well, for a freely floating body, it should be equal to the displaced volume. There are some off diagonals here because the center of gravity is not at the location where we're defining our rigid body modes about. So that just says print the structural mass matrix. This is the structural mass matrix. And then returns back to the calling file, which is box0.txt. So then we're finished with this command, with this line here. And the next line is where is hide_analysis, where we determine the added mass, hydrodynamic damping, and wave exciting forces. Then in hide analysis response, we use those values, the added mass, damping, and exciting forces, to solve the equations of motion, to form and solve the equations of motion to obtain the response. Hide post-response and hide modal pressure are post-processing commands. Hide post-response allows us to calculate the potential, the pressure, and the displacements, or any combination thereof. You can look at the help file for the syntax for this command, as well as for this hide modal pressure command. Now, I don't usually use these commands, honestly. I've put them in here to demonstrate that they are available. Okay, now we want to calculate the transfer functions for the 6 rigid body motions. So we first want to define a modal matrix, so-called modal matrix, which tells us what exactly we want to calculate. And you can refer to the manual for what this command does, but essentially at the baseline, we would say we would have a 6x6 identity matrix to recapture the 6 rigid body motions. However, the rotations are calculated in radians, of course, and we want to convert those to degrees, because it's easier to interpret. So what we want is a diagonal matrix. The upper 3x3 is an identity matrix, so that gives us the surge, sway, heave transfer functions. And then the lower 3x3 submatrix is going to have the conversion factor of 180 over pi to convert from radians to degrees. And that's what I've done here. First I've defined a temporary variable of 180, and I've defined pi, and then I've dividing 180 by pi, and then I'm putting that in the location 4, 4, 5, 5, and 6, 6 of this hide mode mat. And then I remove this temporary variable because I don't need it anymore. Hide TF calculates the transfer functions. And if we come to the help file for this, let's just go to that. There are some arguments here and some parameters that can be specified. So I'm not using any, so I'm just taking the defaults for all of this, all of these values. So, and what it does is it's going to put the transfer functions in an array called hide_TF, and it's going to write it
to a file with the extension TF. So we'll see that in a minute. After we run this, we'll see that. Now the transfer functions are complex, and oftentimes we want to look at the RAOs, the response amplitude operators, which are the magnitude of the transfer functions. So I'm going to take the absolute value of the transfer function and call that RAOs naturally. And we're going to use that in a little bit, and you'll see why I'm doing this now. Now I also want to calculate a vector with the wave periods. So HYDRAN works with frequencies, so it's converted, although we input periods, it's converted those to frequencies and saved just the frequencies. It doesn't save both because then there could be some inconsistencies that show up. So what we want to do is we want to calculate the wave periods as 2 pi over omega, and we're going to use those later, as you'll see. So first I copy the frequencies to a variable called wave periods. I take the inverse of that, so I have 1 over omega, and then I multiply by 2 pi. And so then wave periods contains, the wave underscore periods vector contains the wave periods. And then HYDWET calculates the estimates for the wet natural frequencies. And what it does, I'm not going to go into this in a lot of detail because I do discuss that in a different video. And save just saves the database for future use, and return returns back to interactive mode. So I think that's kind of clear, and so let's run this thing, and we can see that it's very fast. It's finished. If we come back here to let's see, come back here to this command here. Sorry, not that command, this command, hide body check. Now I said it was very important to use this command to check some basic output. And so what it does is it based on your mesh, it calculates the displaced volume. And that should be, and it does it 3 different ways: X projection, Y projection, Z projection. And those should give pretty closely the same values. And of course, because this structure is just a box, it actually gives identical values for all 3 cases. Also calculates the surface area. The center of buoyancy in inertial coordinates, it also calculates, and that one should know what that is for your structure, and one should make sure that these values are consistent then with the values you know that should be there, because again, it's a check on your mesh. The input coordinates for center of gravity, well, that's just what we input as the input for the center of gravity. But it does check to make sure that the center of buoyancy, it does compare the center of buoyancy and the center of gravity. And for a freely floating single body, the center of gravity and the center of buoyancy have to be vertically aligned on the same vertical line, and which is confirmed here with basically 0 for the X difference and the Y difference in those coordinates. The Z coordinate can be different. It typically is different, and it's given here. It is 9.38. I also wanted to come back here to this command on hide node tolerance, and what it does is notice it has found these 2 nodes where I changed the Z coordinate to be a little bit above or a little bit below the still water line. And what it's saying is, okay, it found for node 4, it found that the Z coordinate was 5 times 10 to the minus 4. That was less than the default tolerance, and so it changes it to 0. And similarly for node 25, it found that it was slightly below the still water line, and it changed it to the still water line. So this is the output for the HYDRAN analysis command, where what it does is calculate the added mass, damping, and wave exciting forces. So that is all of this stuff. It tells you it for each wave frequency and wave heading. Of course, only the wave exciting forces depends on the wave heading. And then HYDRAN analysis response gives some programs, some summary values, and then it calculates the response for each of the wave angles and wave periods. Now, we want to look a little bit more at the HYDRAN-TF. So if we look and see what has been created here, so LS gives a listing of what's in the database, and a name that starts with a period, a dot, is created internally. So you should never create your own variables with a dot, because you might conflict with something, a name that the program is using internally. So the transfer functions are in HYDRAN-TF. So if we do a long listing for HYDRAN-TF, we'll see that it's complex. And if we do the same for RAOs, we'll see that it's real, which is what we would expect, right? Of course, they're both three-dimensional arrays. The first dimension, 8, is the number of wave periods. 2 is the number of wave angles, and 6, there's for each of the 6 rigid body modes. So let's, right now on the database over here, it's blank, because what we need to do is we need to load the database from the program to the GUI. So basically all of this is now in the GUI here, and what I want to demonstrate is how we can plot the RAOs. But actually before that, what I wanted to do is I wanted to look at the mesh. So normally I would put a return after creating the mesh, and then view the mesh and check the results from HYDRAN check before proceeding further with the hydrodynamic calculations. So I would make sure that the mesh is correct. I didn't do it here because this has been vetted very, very well, so I knew there weren't any errors with the mesh. But I do think it's useful to show that this is the mesh right here, so we can move this over here. So like I said, it's just a box. This is a very coarse mesh, not sufficient for practical purposes, but we can see that the mesh looks fine for our purposes, and so it's a good tool to inspect the mesh. Notice that the green indicates the wetted surface. All right, let me close that. Now let's look at what we want to do is we want to plot some of the RAOs. So we come down here. This is what we want to plot. So we come up here. We want to do an XY plot, right? So let's plot. Let's say we plot heave, and that's going to be I'll just say heave RAO, and we're going to plot it versus wave period. So wave period, and that's in seconds, and y-axis label I'll just say heave, and that's meters per meter amplitude wave. So heave is the third degree of freedom. Surge is 1, sway is 2, heave is 3, roll is 4, pitch is 5, and yaw is 6. So in the RAO, what we want is the third table, if you will. If the first, if this 1 here corresponds to the first table, second table, third table, up to sixth table. Then we want to plot the third table. And we want to plot, well, we'll plot both 0 degrees and 45 degrees. So first is going to be 0 degrees, and then the second one is 45 degrees. And now our wave periods are in a different array. And so the drop-down menu only lists real vectors. And so it lists .hide frequency, but we want to do .wave periods. And we're going to use the symbols. And I believe we're good to go here. So this allows us to use an X that's in the array that we're plotting, but that's not what's happening. We're using a different vector for our X values. And so that's for heave, and we can, let's plot surge. Surge, well, RAO, or, well, okay, surge, RAO, wave period, seconds, surge, again, meters per meter. We're going to use table 1, we're going to wave periods, 0 degrees and 45 degrees, and there we have that, and here we have the surge RAO, and let's plot sway as well. So let's do here sway RAO. Really, we don't need to put this in. I mean, if we're just doing some simple checking of the, but I'll do it here, meters per meter. By the way, if we were doing roll or pitch, we would have degrees per meter because we converted to degrees, right? So 1, 2, let's see, we're doing sway, that's 2. And we're doing wave periods. So we're using the wave period, values in the wave periods. Sway is table 2, and 0 degrees and 45 degrees. All right, so in 45 degrees, or in 0 degrees, we know sway is 0. All right, so that is the end of box 0. The next, if we look at the other sample problems in this folder, we'll see that there's also a box 2, which implies that we're going to be using double symmetry. So we'll take a look at that next. Okay, now we're going to look at the exact same structure, except we're going to be using double symmetry. The box is symmetric about with respect to the XZ plane and the YZ plane. So we can use double symmetry in this case. So those two files are box2.txt and box2-gen.txt. I have them open up here. So this is box2.txt, and essentially the only change in this file, the only necessary change in this file, is the symmetry code is changed to 2 to indicate that we're using double symmetry. The big change is, of course, in the mesh description, because we only need to describe the upper right-hand quadrant of the structure. So if we look at this, the number of nodes are reduced, of course, but the commands are the exact same. Specify the nodal coordinates, and now you notice that we use a different, just to demonstrate the different options for specifying the nodal coordinates. We're using the sort of a more modern approach of defining the panel, or sorry, in this case, the node number,
the x-coordinate, y-coordinate, and z-coordinate. And then we again do hide node tolerance. We also have some nodes that are slightly offset to demonstrate that. The panels are here again, a little bit more modern syntax for the specifying the panel ID and the node number. Note that, or the nodal connectivity. Note that the panels don't need to be sequentially numbered. There's a gap here. This number here just has to be equal to or larger than the maximum panel ID number that's specified. Again, hide body check, hide export graphics to show the mesh, hide rigid modes, all the same commands, hide our mask. The mask matrix is the same for, that doesn't change, that's the same, it's the mask matrix for the entire structure. All right, so let's run this and we'll see that we're not going to spend a whole lot of time on this because it's the exact same thing. It's just we're just using double symmetry is all. So I need to change this to box 2 and type in and then file in. And we're done. So what I want to do is let me scroll back up here. I could look in the output file, .out file, but I'll look here. So in this GUI here, again, hide body check. Important to confirm that these numbers should be the same as the previous numbers, and they are if you will check them. The tolerance here, we see that it's found some nodes that are where the they're within the tolerance for what it's expecting. So, for example, it's not expecting any coordinate with a y value, any node with a y coordinate less than 0, right? Because we're defining the upper right-hand quadrant, if you will. And so all of those are, so everything should have a positive x, positive y coordinate. And so it's fixing nodes that are within the tolerance, the default tolerance of this command. So let's see here. Hide export graphics. I want to show the mesh. In this case, we have box 2 mesh. And we look at this, and we're looking at the that upper quadrant, that upper right-hand quadrant. So I don't know if you can kind of see it, but we're looking, so this is X, this is Y, and we're looking at the inside of the box because that's our view angle. So if we rotate it, we see we can kind of see what we're talking about here. We've just got 1/4 of that box. All right, so and some of the panels are above the still water line. You can put panels above the still water line for visualization purposes. The program just ignores them in terms of computation because there's no water there. And that's pretty much it. Everything else is the same. It's just that the mesh is different. And so next, if we look at the panel or the problems we have in this file folder, we have, where is box 1 2 module, box 1 3 module, box 2 3 modules. So we'll do box 1 2 modules next. All right, now let's do the 2-body example. So these are 2 unconnected bodies. This is described in the PDF file introduction that we talked about earlier in this video. We have 2 unconnected bodies. Each body is identical to the box that we considered before. Because the system is not doubly symmetric, we can either use no symmetry or single symmetry, and we're going to use single symmetry in this case. The boxes are arranged serially along the inertial x-axis.
And the origin of the inertial coordinate system is located at the center of body 1. And the center-to-center spacing of the boxes is 1,000 meters. All right, so let's come back to the input file. I already have that open here. And see what's different. So on the hide parameters command, the two things change. One, we're specifying that we're using single symmetry. And two, we're specifying that there are two bodies now. So this is a problem that involves structure-fluid structure interaction. So the presence of body 1 affects the motions of body 2 and vice versa. But they're not connected mechanically. So because there are two bodies, we need to specify the hide coordinate axis twice, command twice. Once for body 1. In that case, that's the same as before. The body fixed coordinate system is at the origin of the inertial coordinate system. And then we need to specify it for body 2. So the body fixed coordinate system in the inertial coordinate system is the origin of the body fixed coordinate system is at 1,000, and then z is 0, and y, of course, is 0 as well. And ZCG in the body fixed coordinate system is still the minus 10.62. What's different here is we have this origin equal to 1,000. So the reason that's there is because we're going to specify, we don't have to do this, but we're going to specify the nodal coordinates of body 2 as if it were at the origin of the inertial coordinate system, just for simplicity, because we already have those nodal coordinates and so forth. But then we need to have the program shift those coordinates to basically 1,000 meters ahead to where the origin of that where that body is. And so this exemplifies that there's a possibility for a third coordinate system. We know there's an inertial coordinate system. We know there's a body fixed coordinate system. And there's a possibility for a third coordinate system, and that's the input coordinate system for the mesh. And that's what's different here. So we need to specify that shift. In this case, we're looking at 3 wave angles, 0, 45, and 90 degrees. And again, 8 wave periods. Here are the nodes for both body 1 and body 2. You'll see that if you look down here, there are no x coordinates that are like 1,000 or around 1,000. That's because we're specifying them back to the origin, because we just wanted to reuse the coordinates basically. But what we do need to do is we need to then issue this command, hide coordinate transform, telling it to transform the coordinates for body 2, which has nodes 34 to 66, according to the specification up here by this hide coordinate axis command. And then the panels are defined for both the bodies. And now we need to specify hide body check for both bodies, body 1 and body 2. So for body 1, we tell it, okay, body 1 involves nodes 1 to 33 and panels 1 to 24. Similarly, we tell it the body 2 is represented by nodes 34 to 66 and panels 25 to 48. Similarly, we want to generate the rigid body modes for each body individually. So we specify the rigid body modes for body 1 and for body 2. And then we export the graphics so we can view it in the GUI. We need to specify the mass matrix for body 1 and body 2 independently, because in this case, of course, the two bodies are identical, but of course, generally usually they're not going to be identical. So we need to specify the mass matrix for each body individually. And then hide analysis calculates the added mass hydrodynamic damping and wave exciting forces for the structure being both bodies. And hide analysis response calculates the response, the motion response. All right, so let's run this. Now, instead of starting HYDRAN-XR over again, I'm going to use the option of changing project here, and I'm going to box1 _ 2 mod, use this project name corresponding to the input file. You don't have to do that, but I find it convenient. And then file in. All right, so that's done. So let's look at the mesh, so kind of we can visualize things a little bit better. And in this case, we need to come down here to box1 to mod, and here is the mesh. So we need to this is body 1, that's body 2. The origin of the inertial coordinate system is back here at the center of this of body 1. All right, so now we kind of see what we're talking about here. We've got two bodies. They're not connected. We're using single symmetry, so we're just looking at the positive y space. And close that. And, you know, everything else is the same. So if we look at what's available, you know, everything else is the same. We didn't do hide TF. We didn't calculate the transfer functions. We could have, but I mean, it would have be the same, except we now have 12 degrees of freedom. And so if we were going to develop a Hyde mode mat, we'd probably want to use a 12 by 12 matrix to calculate the transfer functions for each body, you know, the 12 degrees of freedom. All right, so if we come back to the sample problems, we've done box 1-2 mod. We're next going to look at box 1-3 mod. Now we're going to look at a three-body problem. There are three bodies. Each body is identical to that box that we looked at before. So one body is at the origin of the inertial coordinate system. One body is 1,000 meters ahead, and one body is 1,000 meters behind. So this example is described in Appendix A2 in that introduction.pdf file that we talked about before. So this discusses the no symmetry case. We're going to look at the single symmetry case right now. But it's essentially the same as before, so we're just going to look, this will be fairly quick, we're going to look at the changes to the input file that are necessary for this case. So let me come down to BB Edit. I've already opened the file, box 1-3 mod, so the 1 means we're going to be looking at single symmetry. All right, so the changes. We now have three bodies. The inertial coordinate system is going to be at the center of body 2. So body 1 is going to be 1,000 meters ahead, and then body 3 is going to be 1,000 meters behind. So now we need to have three instances of the Hyde coordinate axis command. One for body 1, body 2, body 3. And this is the same as before, as we saw. It's 1,000 meters ahead, and the body fixed coordinate system is 1,000 meters ahead. Body 2 is at the origin of the coordinate system, and there's no shifting of coordinates and so forth. And body 3 is 1,000 meters behind, and again, we're having a different input coordinate system than the body fixed, or the inertial coordinate system. So we need to do a transformation. We're going to again looking at three wave angles and 8 frequencies. Here are the nodes. They're all given as if each body were at the origin of the inertial coordinate system. But then that means we need to transform the coordinates for body 1 and body 3 so that body 1 is 1,000 meters ahead, and body 2 is 1,000 meters behind. Or excuse me, body 3 is 1,000 meters behind. Here are the panels, and we have a height body check for each body. We define the rigid body modes for each body, and we define the mass matrix for each body. Here we have identified a Hyde mode matrix. There are 3 bodies, 6 degrees of freedom per body, so there are a total of 18 degrees of freedom. So it's an 18 by 18 because we want to capture the transfer functions for all 18 rigid body modes. By the way, body 1 will have degrees of freedom 1 through 6, body 2 will have degrees of freedom 7 through 12, and body 3 will have degrees of freedom 13 through 18. And then everything else is the same. Now, the one difference here is that when we calculate the transfer function, because we didn't change Hyde mode mat to convert from radians to degrees, our transfer functions for the rotational degrees of freedom will be in radians. All right, so let's run this. And before, instead of restarting HYDRAN-XR, I used the option of coming up here and saying change project. Well, if you looked, then this will automatically save the database for this the current problem. To get around that, it's not a big deal for these small databases, but if it's a big database, then it can be a little bit more, take a little bit more time to save that database. So we can just type in a new project here, and that will not initiate a save database command. So the command there, the input file is box1_3 mod, and then file in, and it's done. All right, so if I do an ls here and we look at HYDTF, we see that it's 8 by 3 by 18. So that's the 8 frequencies, 3 wave angles, 3 wave headings, and the 18 degrees of freedom. I realize I forgot to put in the command to export the graphics file. So let me do that from the command line here. I will add that to the input file later. All right, so now let's look at the mesh. We want box 1-3 mod. And let me make this bigger so we can. Let me zoom back. Okay, so I think you can get the idea here that we now have a single symmetric mesh. This is box 1, box 2, box 3. The origin of the inertial coordinate system is here. And this is the problem we're solving. Again, there are 3 unconnected bodies. So we have a structure-fluid structure interaction problem. All right, so what is left? I believe there's only one problem left, and that is box 2-3 mod, and we will consider that next. I just realized that I forgot to do one of the examples that I should have done before box 1-3 mod. And that's box 0-3 mod, the zero symmetry case. So let me do that real quickly. Here's the input file. Again, the only difference really is that symmetry is equal to 0, and then of course we need to specify the nodes and panels for the entire mesh, not just a symmetric portion of the mesh. But all of this is the same as we saw before for box 1-3 mod. If we scroll down here, we have the coordinate transformation, the panels.
All right, so let me run that real quickly here. I'm going to do a new project. Box 0_3 mod. File in, and it's done. And all we're going to do is check the mesh. So box 0-3 mod. Convenient. Okay, here is the mesh. Where is that third box? There it is. All right, so you can see we've got box 1, box 2, box 3. The x-axis is this way, y-axis is this way. This is at the center of the box 2, which is at the center of the inertial coordinate system. We can rotate it around. We see, of course, there everything is good to go. So the results will be within numerical precision, the same as for box 0, box 1, box 2, 3 mod case. All right, let's finish this up with the last case, and that is box 2-3 mod. In other words, we're going to look at the 3 module case using double symmetry. So the only difference here is that symmetry is equal to 2 instead of symmetry equal to 0 or 1. So let's think about this for a minute. This is a doubly symmetric module or model. So we are only modeling the first quadrant. So that means we're going to be modeling half of module 1, that's in the positive y direction, and a quarter of module 2, which is in the positive y, positive x direction. And we're not going to model explicitly module 3 at all, right? So we come back down here. We do still need to specify body 3, and the nodes, of course, are in the panels are only going to be for the section, the model that I just described. So we're not inputting nodes and panels for module 3. So we only need to do a coordinate transformation for module 1. Now, similarly, we can just do height body check for bodies 1 and 2. This will become a little clearer when we talk about height export graphics. And we're going to generate the rigid body modes for module 1 and module 2. And now we're going to use this option here where we're saying, okay, we're going to reflect body 1 to represent body 3. So we still have 3 bodies, so we have the 3 mass matrices. And so now this is where the complication comes in when we want to use symmetry. And honestly, if you want to use symmetry when it becomes this complicated like this, I would say think about it. The advantage of symmetry is it uses less computational power, less computational resources. The disadvantage is it typically requires more work on the analyst's part. So it's a trade-off. So if you've got sufficient computational resources to avoid using symmetry, you might think about doing it that way rather than using symmetry just to save computational resources that you already have. I mean, you don't need to save. So the issue here is that we need to describe the motion in terms of symmetric and antisymmetric modes of motion. So for single symmetry, the surge, sway, heave, roll, pitch, yaw of each individual module was singly symmetric or antisymmetric. So for example, surge of module 1 is symmetric about the XZ plane. When we get to double symmetry, though, surge of module 1 is symmetric about the XZ plane, but it's not symmetric about the YZ plane. So we need to form modes of motion which are symmetric or antisymmetric. So, for example, a surge of module 1 in the positive x direction and surge of module 3 in the negative x direction, that's going to be symmetric about the YZ plane and symmetric about the XZ plane. So it's symmetric. And we need to describe the 18 degrees of freedom in terms of combinations of these modes that are going to be symmetric, 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 anasymmetric, anasymmetric, symmetric, anasymmetric, anasymmetric. So that's what this underscore psi matrix is. It's a matrix which takes those individual 6 rigid body modes for each module and combines them in a way that we create 18 symmetric / antisymmetric modes. And then we need to use the HYDRAN-modes command, which tells it, okay, mode 1 is, in this case, symmetric antisymmetric. Whoops. Symmetric antisymmetric. Mode 2 is symmetric symmetric, etc., etc. So this is why it's a little bit more complicated to in this case, to consider double symmetry. All right, so other than that, we can proceed with the hydrodynamic analysis. So I'm not going to go further into this. I will delve into this a little bit more in more detail when I talk about the mobile offshore base examples that are in the testing folder. All right, so let's go to, let me just do this, run this. Let's see here, what is this? This is box2_3 mod, file in. Okay, let's look at the mesh. So we come here and it's box2-3 mod. Here we go. And all right, here we go. This is it, right? This is 1/4 of module 2 and 1/2 of module 1. Module 3, which is in the negative x direction, is not explicitly modeled because it's dealt with through symmetry. I'll try to rotate this to show you what we've got here. So you can see what the wetted surface here is. So I'm not going to go into any further detail. We can get the exact same results from all 3 cases: zero symmetry, single symmetry, double symmetry. It's just an issue of which one you want to use.